In this video, I'm going to discuss confidence intervals for population proportion, and we'll do a few examples where we actually calculate some confidence intervals for population proportion. Okay, so first off, remember what this is. So we have between 0 and 1, we're somewhere in this interval between 0 and 1, there's the sample proportion, and there's the population proportion, right? So say the population proportion is, say it's here. Okay, remember population proportion we note with just a p. All right, so you go out and you get a sample, and so say your sample proportion comes out to be here. So here's p hat. Now you'd hope that p hat is close to p. It's unlikely that it's going to lie exactly on where the population proportion is, because, well, you only collected a sample. You didn't collect every piece of data in the population. As you increase your sample size, the likelihood of this being closer and closer to where the true population proportion is, obviously it will increase. Okay, well, so what is a confidence interval? What we do is we build an interval around p hat. Okay, so we go a certain direction above and below p hat. The amount that we go above and below, it's called E, the margin of error. Okay, so we go E above and E below p hat, and we create an interval. Now, we're 95% confident that this interval, say if we're talking about the 95% confidence interval, then we're 95% confident that this interval contains p, right? If we're talking about a 98% confidence interval, then we're 98% confident that this interval contains the population proportion p. Right? So depending on your confidence level, that tells you how confident you are. Okay, so let's go ahead and write down some equations for these guys. First off, what is p hat? P hat is the number of successes divided by the number of trials. Sometimes people will just write it as x over n, right? Where x is just the number of, so for example, if you're trying to calculate the proportion of people that enjoy to drive, right? You would say, okay, well, how many people enjoy to drive divided by how many people did you sample, right? So this is p hat, sample proportion. Then there's this equation for E, the margin of error. Okay, so this equation for E involves the critical value, Z alpha divided by 2, which this critical value purely depends on what your confidence level is, right? So if your confidence level is a 95% confident, for example, Z alpha divided by 2 will always be the same number, right? So let's see, Z alpha divided by 2 times the square root of p hat times q hat over n. Okay, so square root of all of that. Now remember, q hat would just be 1 minus whatever p hat is. Okay, so once you have that, you're ready to go ahead and build your confidence interval. So the confidence interval is just p hat minus E. Okay, so go a certain direction behind p hat. So p hat minus E, and then put the population proportion in the center, and then p hat plus E. Okay, so whatever your confidence level is, say it's 90%, then you would say, okay, well, I'm 90% confident that the population proportion lies within this interval. All right, first let's talk about some requirements in order to be able to use this interval, and then we'll do some examples. So the first requirement is that the sample must be a simple random sample. Okay, you can't have a biased sample. You can't have a sample where one person's response to a survey or something makes the next person respond differently, right? So there must be independent sampling, and the sampling must be at random. Okay. Conditions for the binomial distribution must be met, which the binomial distribution assumptions are there are a fixed number of trials. So in other words, you can't collect some data and then say, oh, well, actually I need some more data, so then go out and get some more, right? The binomial distribution assumption is that there's set beforehand how many trials you're going to do, right? So that you can't can say, well, I'm interested in the proportion of heads when I flip a coin, and I'll flip it 5 times, and then you realize, well, I wanted the proportion to equal 0.5, and it doesn't because I only flipped it 5 times. So I'm going to flip it now 50 times, right? So that's kind of changing the number of trials as you're going in your experiment. So you can't do that in order to use this confidence interval. And actually, you can't do that if you're trying to use anything related to the binomial distribution. All right, the number of trials are independent, right? This is kind of, this criteria would kind of be met by the fact that you have a simple random sample. So, you know, one person's response to a survey cannot influence another person's response to a survey, for example. There are 2 categories of outcomes, right? So either success or failure. You know, either if you're looking at the proportion of people who enjoy driving, then either you enjoy driving or you don't enjoy driving. There's no other option. Okay. The probabilities remain constant for each trial, right? So this is kind of like, you know, if you were to be flipping a coin, you can't just like change out the coin halfway through the experiment with a weighted coin, right? So the probability must remain constant for each trial. All right. One last criteria is that there are at least 5 successes and 5 failures. This requirement is related to the central limit theorem. Right, basically having a large enough sample size in order to use, basically you're using like a approximation to a normal distribution. You can tell that we're using some sort of approximation to a normal distribution because we're using the variable z. Remember, z is standard normal. Okay, so in order to use that approximation to the normal distribution, you must have at least 5 successes and 5 failures. All right. Let's go ahead and read through this first example. Let's calculate our first confidence interval. In a recent survey, 487 out of 1,000 likely voters reported that they support the Democratic presidential nominee. Find the 95% confidence interval for the population proportion to support the Democrat presidential nominee. Okay, so the first thing I'm going to calculate is p hat, which is x over n. So in this case, x will be the number of people that support the presidential nominee. Looks like that is 487 out of 1,000. Okay, so p hat in this one is just 0.487. All right, now let's calculate E. All right, so this is the equation for E. P hat Q hat divided by N. All right, so in order to calculate E, I kind of need to calculate what the Z guy is first. Okay, so let's actually start by calculating Z alpha divided by 2. All right, and like I said, Z alpha divided by 2 will depend on what your confidence level is. Here we're trying to calculate the 95% confidence interval. So 0.95 is in the center. And so we're looking for the critical value, so this cutoff here, that is Z alpha divided by 2. Remember, this one over here is the same number, it's just negative, right? Because this is the distribution of Z, which is centered on 0. All right, so let's see. First, we should figure out how much area we have in the tails. So 0.95 is accounted for in the center. Then we should have 0.05 in the tails. So 0.05 in the tails. And we should divide that by 2 because we have 2 tails. So that's 0.025. 0.025. All right, so when I'm going to look at my table, I should look up the value of Z for which the area behind that Z value, is 0.95 plus 0.025, which is 0.975. All right, so let's go ahead and pull up our table. All right, so now we're looking for where the area is 0.975. 0.975, and we're looking for the corresponding Z value. There we go, here it is, 0.975. The Z value that corresponds to that is 1.96. 1.96. All right, so this Z, alpha divided by 2, is 1.96. All right, great. So let's see. Oh, we should also calculate what Q is. That's another thing that's in this equation for E. So let's go ahead and do that too. So Q would be 1 minus whatever P hat is. Okay, so that's going to equal, so Q hat then will be 1 minus 0.487. Let's go ahead and pull out our calculator for that. 1 minus 0.487 is 0.513. Okay, so equals 0.513. Okay, so now I have everything I need to calculate the margin of error, or E. All right, so let's go ahead and calculate that. So E is going to equal, first I start with Z alpha divided by 2, the critical value, which is 1.96, times the square root of 0.487, right, that's what P hat is, times Q hat, which is 0.513, divided by N, which is 1,000, right? We sampled 1,000 people. All right, so let's go ahead and pull out our calculator again. Let's try to calculate this guy. Okay, so first I'm going to calculate the inside here. Okay, so I'm going to start with 0.487 times 0.513, divide that by 1,000. Okay, press enter. Okay, then I'm going to take the square root of that. Let's press the square root button. Then I'm going to go ahead and multiply that by 1.96 times 1.96. All right, there we go. So notice how when I was calculating this, I tried not to do any rounding. I like to just try to plug this into your calculator in a way that you don't have to do any rounding. Okay, so 0.03097. Okay, so we should round this to at least 4 decimal places. So I'm going to take 0.030, so the 9 rounds it to a 1, 0. Okay, so 0.0310. Okay, so 0.0310. Right, there you go. There's our margin of error. Okay, so now we're ready. Once we have the margin of error, we're ready to go ahead and calculate our confidence interval. So remember, the confidence interval is P hat minus E, and then the population proportion is in the inside, P hat plus E. Okay, so P hat is 0.487 minus the margin of error 0.0310, and then 0.487 plus 0.0310. All right, let's get our calculator and calculate both these guys. So 0.487 minus 0.031, 0.456. Okay, all right, so that's 0.456. Okay, so now let's do the other side. So we have 0.487 plus 0.03110. We get 0.518. So 0.518. All right. So now if we had to interpret this confidence interval, so let's see, this means that we are 95% confident that the proportion of likely voters that support the Democratic nominee is between 0.456 and 0.518. Okay, so now does it appear that the Democratic nominee is going to win or lose the election? Does it appear that they are going to lose the election? Well, if you were to look at P hat, you might say, well, yeah, because P hat sample proportion is less than 0.5, right? 48.7% of the people that were sampled don't or are going to vote for the presidential nominee, Democratic presidential nominee. So that means the Democrats aren't winning. However, if you were to look at the 95% confidence interval, which would be a better way to get at the question, does it look like they're going to lose based off of this sample? If you were to look at the confidence interval, you would say, oh, well, you know, the confidence interval contains values for which the nominee would lose, right? And it contains values for which the nominee would win. So this confidence interval doesn't really tell us whether or not the Democrats are going to win this election or not. And in order to better answer that question, we may need to come up with a bigger sample size, right? If we had a larger sample size, this confidence interval would become more narrow because the margin of error would become smaller, right? Because we're dividing by the sample size, which is 1,000. So as the sample size gets larger, the confidence interval gets more narrow. So it can, it can better give you information about where the true population proportion P lies.